Welcome to the Explainer. So, you're looking to truly grasp how computers organize the digital world, right? Well, you are in exactly the right place. Just imagine for a second you've got this massive pile of physical building blocks. If they're just kind of dumped in a heap, they aren't very useful, are they? But when you organize them, into foundations, walls, bridges, you can build some pretty incredible things. And honestly, the exact same principle applies to computer science. Today, we're opening up the Architect's Toolkit to demystify data structures. We're going to explore how organizing data perfectly is quite literally the secret behind every fast and efficient program we use.
Okay, here's our quick roadmap for this explainer. First, what are data structures? Then, we'll hit linear structures like stacks and queues, followed by nonlinear ones, trees and graphs. Fourth, we'll look at ADTs using a TV remote analogy. Fifth, we'll measure speed and memory. And finally, algorithms in action. Let's get into it.
Section 1. What are data structures?
So, here's the thing. Simply having data just isn't enough. A data structure is basically a specific way of organizing, storing, and managing data in a computer so that it can be used efficiently. And that word right there, efficiently, that's absolutely crucial. It's the core why of everything we're talking about today. Because if your data is stored poorly, your programs are going to run super slow and they'll eat up way too much memory. Data structures essentially give us the blueprints to fix that exact problem.
When we look at the types of data structures out there, they generally split into two main branches. First up, we've got primitive data structures. These are your basic built-in types. Think integers for whole numbers, floats for decimals, characters, booleans, you know the drill. They just hold one single value. But then we have the non-primitive data structures. Now these are the more complex architectures built out of those simple blocks, allowing us to store multiple values together. And these break down even further into linear and nonlinear types, which brings us right to our next point.
Section 2. Linear, stacks and queues.
All right, so in linear data structures, elements are stored sequentially, literally one right after another. The most fundamental example of this is the array. Now, an array is completely static. It stores a collection of elements that are all the exact same type, right next to each other in contiguous memory locations. To grab anything from it, you just use its index starting at 0. It's incredibly fast for accessing data for sure, but the catch? Its size is fixed at compile time. Once you set that size, there's no changing it. On the flip side, a dynamic linear data structure is the stack. Unlike an array, a stack size can actually grow and shrink on the fly at runtime. The defining feature of a stack is that insertion and deletion happen at only one end, which we call the top. When you add an element, it's called a push operation, and when you remove one, that's a pop. If that sounds a bit abstract, just picture a physical stack of heavy books, or maybe a stack of plates in a cafeteria. If you add a plate, it goes right on top. When you take a plate and you grab it from the top. This perfectly illustrates the core rule of a stack, LIFO, or last in, first out. The very last element you tossed on the pile is always going to be the first one you take off. Now, let's contrast that stack with a queue. A queue is also a linear data structure, but it handles things completely differently. Instead of doing all the work at one end, elements are inserted at one side, called the rear, using an NQ operation, and they're deleted from the total opposite side, the front, using a DQ operation. To really cement this one in your mind, just think of a real-world line. Whether it's people waiting at a bus stop or a massive, chaotic line of fans queuing up for IPL cricket tickets, the rule is the exact same. FIFO, first in, first out. The first person to jump in that line is going to be the very first person to get on the bus or snag their ticket. And that is exactly how a queue processes information.
Section 3. Nonlinear trees and graphs.
So, you might be wondering, why do we even need nonlinear structures? Well, let's walk through a quick comparison. Linear structures lay data out in a single, easy-to-read sequence on one level. But because of that rigid setup, memory usage can be pretty inefficient, and you have to traverse the whole thing in a single run. Nonlinear structures, though, they arrange data in these sprawling, hierarchical, or network forms across multiple levels. Yes, they're definitely harder to implement, but their memory usage is incredibly efficient. Plus, they're absolutely essential when you need to represent really complex data relationships. So, first we have the tree. A tree is entirely hierarchical. It starts at the top with a root node, which then branches down into parent and child nodes, creating these really clear multi-level relationships. Then we have the graph. A graph is more like a network made up of vertices or nodes that are connected by edges. These edges map out the direct relationships between the nodes, and honestly, they can connect in almost any pattern you can think of. This makes graphs absolutely perfect for mapping out things like social media networks or city streets.
Section 4. The TV remote, ADTs.
Let's talk about abstract data types, or ADTs. An ADT essentially acts as a boundary. On one side, you've got the application program, so the code you're writing. On the other side, securely inside that boundary is the actual data structure, hanging out in memory. The user never actually touches that memory directly. Instead, they use an interface as a bridge. It gives you access to public functions like push or insert, while keeping the private functions and all those messy memory details completely hidden away. Honestly, the absolute best way to understand an ADT is to think of a TV remote. When you want to crank up the volume on your TV, you just press a button, right? That button is your public function. You don't need to know how the circuit board works, and you definitely don't need to understand the TV's internal logic. The remote is your interface. It tells you what actions are possible, while keeping the super complex implementation safely hidden under the plastic shell. And that is exactly what an ADT does for us programmers.
Section 5. Measuring speed and memory.
Now, to actually measure how efficient these systems are, we use asymptotic notations to look at two big things. The first is time complexity. This is basically just the amount of time an algorithm takes to run based on the size of its input. It lets us pit two algorithms against each other to see which one crosses the finish line faster. When you're dealing with massive amounts of data, knowing the time complexity is literally the only way to avoid forcing your users to wait forever.
So how do we actually write this down? We use big O notation, which you'll see represented by a capital O. Big O shows us the upper bound of an algorithm's running time. Put simply, it tells us the absolute maximum time an algorithm could possibly take, the worst-case scenario. For instance, O of n means the time it takes grows linearly right alongside the size of the input. And by preparing for this worst-case scenario, we make sure our programs don't just randomly crash or stall when the data scales up.
The second big measurement here is space complexity. This is all about the amount of memory an algorithm needs while it's executing. Look, an algorithm could take 0 time to run, but if it demands more memory than your computer actually has, well, it's going to fail. Grasping space complexity helps us conserve memory, which is a total game changer for writing efficient programs, especially when you're working with devices that don't have a lot of storage to spare.
Section 6. Algorithms in action. Let's see this in action with a linear search algorithm. Say we have a linear array of numbers, and our mission is to find a specific key, in this case the number 41. A linear search is super straightforward. It just starts at index 0 and checks every single element one after the other. Is 70 equal to 41? Nope. Is 40 equal to 41? Nope. It just keeps marching down those contiguous memory locations until it finally hits our match.
If we break that code down into simple, logical steps, it goes like this. You read the array, you sequentially compare your key to each element, and if you find a match, you print its position. Now, tie this back to time complexity for a second. If our number 41 was the very first item in the array, boom, we'd find it instantly. That's our absolute best-case scenario, written as O of 1. But if the number was at the very end of the array, or maybe not even in there at all, we'd have to search the entire length of the thing. And that right there is our worst-case scenario, big O of n.
It's fascinating, right? Data structures really are the foundational building blocks of our digital world, and they so beautifully mirror the physical world around us. From cafeteria stacks to that TV remote on your couch, these concepts are literally everywhere. So I want to leave you with this somewhat provocative thought. If everyday objects like bus stops and remotes inspire how we organize data today, what complex, real-world systems are going to inspire the highly efficient algorithms of tomorrow? Keep learning, keep observing, and I'll catch you in the next explainer.